So here we have a graph. First thing we'll do, Oi Zerga. Origin is there. The y-axis is force straightforward. X-axis is time. The intercept's yes. We have a y-intercept equal to 0. We can read force and time. The slope is delta F over delta T, which is the rate of change in force. And the area is F delta T, which we recognize as the impulse, J, which is equal to the change in momentum, which is equal to the mass times the change in velocity. All right, so student records exerted on an object moving in a straight line with a horizontal frictionless track. So if we have a cart on a frictionless track and there is a force applied to it, there's no friction. So yes, there's a force of gravity, and yes, there's a force normal, but those are perpendicular to each other. So the net force is just this applied force, which we can see is variable. It varies from 0 up to this number about 20. Well, if the F net is the sum of the forces, the net is MA, and the sum of the forces in this case is just the force applied. Okay, so that's what we understand there, what's going on there. This thing is going to accelerate. And since the force applied is increasing, while the mass stays the same, the acceleration is also going to increase. All right, so we have that first sentence. Force, best approximation of the change in momentum. Change in momentum is the area between 0 and 4 seconds. Now this is where we need to sort of squint at the data and look at it and see what it's made of. And so maybe we would say it takes this shape and this shape, which means we have a rectangle and a triangle. This side is 2, that height is 10. This side is 2, this height is 10. So this then becomes 20. 10 times 2 is 20, 1/2 of that is a 10 overall. So we're looking at 30 Newton seconds. What we think the area is, and lo and behold, choice B.